Okay, let's do some linearization and differentials problems. Remember with linearization, like it's a fancy way of saying find the equation of the tangent line. That's all we're doing. So there are a couple of different ways I like to think of this. We like to write this. L of x is approximately equal to f of x0 plus f prime at x0 times x minus x0. I'd like to think of this more like y minus y naught equals m x minus x naught. Or another way to think of that, because m is just the derivative, right? So y minus y naught equals y prime at 0 times x minus x naught. If I move that y naught to the other side, and these are all approximately. This is the equation of the tangent line. I'm saying the actual y value is approximately equal to the tangent line. So remember, we've got some curve here. And I'm saying that this value right there is approximately the same thing I would get if I found the tangent line. Now, that's not going to work forever. Like this point on the tangent line looks nothing like the point on the curve there. But nearby some starting point, if I've got something curvy nearby the tangent line and the point will be close. As you get further away, it becomes a terrible approximation. Look at that. That's terrible. But over here, I'm pretty close. And just for completeness, another way to think of all of this is just what is the derivative? It's a slope. Remember, slope is change in y minus change in x. So the derivative at some value is approximately equal to change in y over change in x. And if you multiply this stuff over, you get this. All of this is really just definition of the derivative. Okay, so that was just a refresher. Let me get all this stuff out of our way. Okay, so we want to do the linearization of y equals cosine of x and use that to approximate something near 0. So I didn't write it, but this is a pretty small number. So it's kind of implied here. We're going to do this linearization at x equals 0. Now, pi over 6 is also close to that. I could, if I wanted, do it at pi over 6. And maybe I get a slightly different answer. Like maybe we'll try it both ways just for fun. Okay, so the linearization is the original at your starting value plus the derivative at your starting value plus, or times, sorry, that's times, x minus your starting value. So first I need y at 0. So cosine of 0. You should know cosine of 0. That's 1. Then I'm going to need the derivative. Derivative of cosine is negative sine. At 0, f prime at 0 will be negative sine of 0. You should know that that's 0. So this means the equation of the tangent line of cosine of x near 0 is the original value plus the derivative times x minus the original value. So that went right there. And that went right there. That means cosine of x near 0, only near the starting point, is approximately equal to just 1. So cosine of pi over 12 will be approximately 1. Now, that's not a very good approximation. Like, we can get our calculator out and see that that's not a very good approximation. So I could make sure first that I'm in radian mode here, which I am. And then cosine of pi over 12, there's pi over 12. See, it's a decent approximation, but not great. And the reason we didn't get a great approximation was our derivative at our starting point was 0. So we were approximating the entire cosine curve, which looks like this, with just a straight horizontal line. That slope there is 0. And this is up at the point y equals 1. So we're getting all these values. Even if I hadn't done pi over 12, whatever I'd done, I would have said, oh, they're all close to 1. So maybe let's do at x equals pi over 6 or 30 degrees. And let's see if we get a better approximation. So I'm going to need the original at pi over 6. I need cosine at pi over 6. That's cosine of 30 degrees. You really should know that that's root 3 over 2. I need f prime at pi over 6. So that will be negative sine at 30 degrees. That'll be negative 1/2. So this says cosine of pi over 12 is approximately equal to cosine at my original All right, let me write out the linearization first. I think this will be clear. So the linearization near pi over 6 will be the original function at pi over 6 plus the derivative at pi over 6 times x minus my original x. So that's original x. That's the derivative. And that's the function at the original x. Okay, then now I can plug in pi over 12. And I'll get root 3 over 2 minus 1/2 times pi over 12 minus pi over 6. So that right there is going to be a negative pi over 6. I'll get root 3 over 2 negative 1/2 times negative pi over 6. Or no, I lied. This is negative pi over 12. That's 1 pi over 12 minus 2 pi over 12s. This in the parentheses is negative pi over 12 times a negative 1/2 would be plus pi over 24. So check all the details there. I did a little bit of arithmetic. We can get our calculator out and do root 3 over 2. Second square root of 3 over 2 plus pi over 24. I get 0.9969. And you may remember I've cleared it off the screen now. Cosine of pi over 12 was about 0.9659. So I got a better approximation. Okay, let's play the same game here. We're going to find the linearization. We're going to find the equation of the tangent line at some point we know that's near this guy. This is the whole key is you have to know the actual function value nearby this guy. So whose square root do I know near 101? Well, that would be 100. So we're going to do this at x equals 100. And because we know square root of 100 is 10. I don't want to do this at 0. Like, I got square root. Ooh, if I go all the way out here to 101, if I did the linearization here at 0, I would get the equation of a tangent line that looks like this. By the time I get to 101, the equation of the tangent line would spit out some gigantic value up here. I want something over here. So I'm going to pick somebody nearby who I know is actual value. And then I'm going to use that line to approximate that value. I'm going to get this value instead of the actual value right there. Okay, so the linearization, or I could even say f of x is approximately equal to the linearization, is f at the first, our starting value, plus the derivative at your starting value times your change in x minus your starting value. So that's all that is. That right there is delta x. And if I move this to the other side, that minus that would be delta y. All this says is delta y is approximately equal to the slope times delta x. That's all we're doing. If I were to move this to the other side, move this over there. So it's not about memorizing this formula. It's about understanding this formula. Okay, so this says square root of 101 is approximately equal to square root of 100 minus the derivative, whatever that will be, times 101 minus 100. So I plugged in the guy I'm looking for here and here. Okay, so we need the derivative. F prime of x is 1/2 x to the negative 1/2. So f prime of 100 would be 1/2. Negative 1/2 means bring it down to the bottom, and 1/2 is a square root. So that would be 1 over square root of 100 is 10 times 2, 20. And this is a plus here. I don't know where that was just a typo. That's a plus. The original function value plus the derivative at the original value times your change in x. Okay, I'm going to write that again. So f at 101, square root of 101 is approximately equal to f at 100 plus the derivative at 100 times the one I'm looking for minus 100. F of 100 is 10. Square root of 100 is 10. The derivative at 100 we just found was 1 over 20. 101 minus 100 is just 1. So I get 10 plus, that's, I think, 0.05. So I get 10.05. So square root of 101 is approximately equal to 10.05. Let's check it and see how well we did. Oh, come on. Come on. That is a great approximation. Okay, it's not exactly what your calculator does. Your calculator is not actually calculating square root of 101. This number that it spit out, that number, square root of 101 goes on forever. Where does your calculator come up with this number? It did a very similar process to what we're doing here, only it didn't just keep one value. It did something that's more like, it's a very complicated process, but this is more related to the Taylor series expansion of that square root. This is what we did, is what's called a first order approximation. Your calculator is using a similar kind of argument, but doing a much better approximation. And you'll learn more about those in calculus too. Okay, let's find the linearization of this guy, and let's do it. I meant to have a value here at x equals 1. Okay, so L of x will be g at 1 plus the derivative of g at 1 times x minus 1. So I'm going to need a couple of values. G at 1 will be natural log of 1 plus 1 minus 1, natural log of 1, which is 0. Now I need to take the derivative. Derivative of natural log of anything is 1 over that thing times the derivative of what's inside. So times the derivative of this stuff here, that would be 2x plus 1. So g prime at 1 will be, let's write this would be a little cleaner if I write it as one single fraction. Let's see, plugging in a 1, I'm going to get 2 plus 1. I get 3 over 1 plus 1 minus 1 is 1. I get 3. So the linearization, which is a function, will be g of 1 plus the derivative at 1 times x minus 1. So just for completeness, I'm going to write it like that. So it's an equation of a line. We're always going to get the equation of a line. So what we're saying is, if you were to graph this guy out, the equation of the tangent line at x equals 1 is this. That's literally all we're doing. Okay, now let's do some differentials problem. It's actually the same thing. Linearization and differentials, they're really flip sides of the same coin. So linearization says y equals y naught plus the derivative of y evaluated at x naught times x minus x naught. If I move this to the other side, I just get change in y equals the derivative evaluated at my starting point, that's not times change in x. Now, if I take the limit as delta x goes to 0, because this is really just approximately, if I take the limit as delta x goes to 0, this says dy equals y prime dx. Or in other words, well, another way of thinking of this. Now, remember, differentials are not algebraic quantities. I really can't divide both sides by dx here, but I'm going to pretend I can. I'm going to pretend I can bring this dx over and say that this really says y prime is dy over dx. Now, was I allowed to do that? No. Does it work? Yeah, it still works. Because that's just a fancy way of writing y prime. That's all differentials are. It's really the definition of the derivative, but you've kind of multiplied the dx over. So here, dy is take the derivative, put it in parentheses, 2x plus 1 times dx. Now, what we're really doing here, anytime you have one of these problems where they tell you to plug in a value for dx, we're really just doing this. We're just doing linearization where this is a delta x. We call this little dx, but it's really not. This is really a change in x. All we're really finding here, is the linearization, the equation of the tangent line, only I'm not looking for the new y value. I've moved this guy over and I'm looking for the change in y. So it really is the same problem we just did, only instead of finding a new y value, I'm finding a change in y. So dy at x equals 2 will be, plug in my x equals 2 here, and I'll get what? 4 plus 1, 5 times my dx, 0.01. So we get dy is, what is that? 0.05. What that means is at this function, at x equals 2, so x squared plus x has a root at 0 and a root at 1. His graph looks like this. Right here at x equals 2, and let's see, we just said that y value was 5, right? If I were to slightly change my x value, if I were to go over to, say, 2.01, then my y value would go up, my change in y, that's a little bracket there. That's not a 3, that's a, look at that distance. My change in y is approximately 0.05 for a change in x of approximately 0.01. So this was my change in x of about 0.01. That's all we're doing with differentials. Okay, now this is saying, this, it looks, this, even when I took this class, this confused me. What's the difference between these problems? This is saying, I don't want approximately. Let's find the actual change in y. Let's find the actual new y value and subtract the two. So these are actuals. So I'm going to need y at 2 and y at 2.01. And then I'm just going to subtract those two. So this we just found, that was 5. That's 2 squared plus 2. This will be 2.01 squared plus 2.01. I'm plugging these values. These are two x values. I'm plugging them in to the function. So 2.01 squared plus 2.01. 60501. Is that right? Okay, I was getting a completely different answer, and then I realized, oh, it's right here. That 5 that I wrote there, no, the derivative at 2 was 5. Here I want the actual function value. I even wrote it out. 4 plus 2 is 6. My actual function value right there is 6. Sorry, 6. And the actual second y value is 6.0501. So this guy here said the change is approximately 0.05 using differentials. The actual change, just y2 minus y1. 6.0501 minus 6 is 0.0501. Come on. Come on. The differential gave me a very good approximation for the actual change. That's all we're doing here when we do differentials, are approximating. We're approximating, instead of a new function value, a change in function values. Okay, and a good place to do this is in these word problems. This is where this is up in the real world. So I've got a cube here. So I'm going to do like the old second grade way of drawing a cube. Each side is about 5 inches. But there's a little bit of tolerance. The machine that makes this can't do it perfectly. There's a little bit of wiggle room in each side. I want to estimate what's the error then in the volume of this thing? So volume of a cube as a function of the length of a side, that's an S, is S cubed. So dV, taking the differential of both sides, will be 3S ds. Or another way of saying that is dV ds. The derivative of this, 3S squared, sorry, 3S squared. The derivative of this guy with respect to S is 3S squared. So if I just said take the derivative, you might say V prime equals 3S squared. A better way to think of that is dV ds is 3S squared. And then the differential dV is, you can kind of pretend you're just multiplying the ds over. dV is 3S squared ds. So then dV evaluated when S equals 5 will be 3 times 5 squared times my ds, my unknown, my error in the side length, 0.01. So that's 75 times 0.01. 0.75. Now, this is we're estimating an error and change in volume. Volume is in cubic units. So this would be inches cubed. So this machine can get within an accuracy of 1/100th of an inch when it machines out a cube. So what's the approximate then maximum error in our volume? About 0.75 cubic inches. The whole thing has an error of 125 cubic inches. With this approximate error, like that's an error bound. Our volume might be that much too high. It might be that much too low. We don't know. We're going to do a similar problem like that here, where we actually do find the two different volumes and see what the maximum error will be. We'll actually have to calculate 3 volumes. Okay, so we've got height of a cylinder. There's our differential. I want to talk about the volume of a cylinder, and they'll give me the radius. Oh, I need to fix this. This is the height. That's a typo. I should say height is 10 centimeters and radius is 5. So I've got some cylinder here. So the height is 10 centimeters. Radius is 5 centimeters. Volume of a cylinder is pi r squared h. But I don't know the radius perfectly. No, I don't know the height perfectly. The height has some wiggle room in it. So we take the differential of both sides. R is a constant here. Pi is a constant. See, they don't tell me that the radius might be off. Our machine somehow gets the radius correct. It's the height that it has trouble with. So my differential volume will be, this is just a constant times h. The derivative of this, so I'll put here v prime times dh, or dv is pi r squared dh. The derivative of a constant times h is just a constant. R is a constant for the purposes of this problem. So then dv evaluated when r equals 5, h equals 10 will be pi times 5 squared, 25, times the differential in h, 0.1. So let's throw that in a fancy calculator here. Times 25 times 0.1, right? I think it was 0.1. Yeah. So 7.85 cubic centimeters. So that's an approximation of how much error we might have in the volume. Now let's actually calculate what that maximum error really would be. So this is just a shorthand, quick and dirty way to estimate a maximum error. So the actual volume, if the machine did it right, the volume when R equals 5, H equals 10 would be pi times 25 times 10, R squared. So I think it's just that last one times 100. But let's write this out. Pi times 25 times 10, or 250. 785.30. Let's call that 785.4 cubic centimeters. So that's if the machine did everything perfectly. That the machine may have made it too big. So maybe the machine messed up. The radius it's getting right, but maybe the height was 10 plus that extra, 10.1. So this would be pi times R squared, 25, times 10.1. So pi, I'll actually type it out, times 25 times 10.1. 793.25. So that's the biggest volume we might end up with if the machine accidentally had the height being 0.1 centimeters too high. But what if it was too low? Because that error, that lack of accuracy could happen in either direction. What if H is 9.9? 0.1 right here. So the minimum volume I might end up with on this cylinder would be that guy. So times 25 times 9.9, 870.85. That seems low. Oh, because I typed, all right, it seemed wrong. I typed it wrong. Pi times 25 times 9.9, 777.54 cubic centimeters. So this is what it should be right here. So the maximum error is going to be whichever possible error is bigger. So we're going to have to find both errors. So the upper error, if the machine makes this thing bigger than it's supposed to be, then the maximum error we're going to have in that direction would be 793.25 minus 785.4. So this is top, this is bottom, and this one's right in the middle. It's what it should be. That's the highest it would be. That's the lowest it would be. That error would be, let me write these both out and then we'll calculate them. And then the bottom error would be the one in the middle minus the number on the bottom. Now, another thing we could do, by the way, like we'll calculate both of these, but something you do in the real world is you might take the average of these two and call that like an expected error, something like that. But here we're trying to find what's the biggest possible error we might end up with. So we got to figure out which one of these errors is actually bigger. We might be too big on the top end, or we might be too small, and that would be an error as well. Okay, so let's calculate both of those. 8 minus 785.4 and 785.4 minus 777.54. So I get 785 and 786 cubic centimeters. So which one's bigger? This one. So the maximum error that we might end up with in the volume is 700 or 7.86 cubic centimeters. Now, what did our differential tell us to expect? It said your maximum error is going to be around 7.85 cubic centimeters. So the differential, look how much less work that was. And it was just an approximation, but it's a pretty good approximation as long as delta H here is small. Okay, that's a good place to stop.